Good evening, friends. Today we are going to see this exercise finite state machine modeling for a thermostat with the two states heating and cooling. So, this we will be creating right from the beginning to the end using a tool called as Ptolemy II modeling tool. Actually, this finite state machine modeling is used for cyber physical systems, and particularly this tool Ptolemy is used for cyber physical systems, wherein we can able to do the system modeling. So, in this example, we are going to model a thermostat with the two states cooling and heating. Now for that, first we create a graph editor. So we open the Ptolemy software and we use a graph editor. So this how the way you will get a graph editor. So generally in this graph editors we can able to create so many parameters, and first thing we have to select is the directors. So what kind of director it is? Now it is synchronous data flow. So that's why we will be using a synchronous data flow director. So we will using just drag and drop that SDF director. So we are going to use SDF, that is synchronous data flow, and we create one more actor called as composite actor or FSM actor. So two things will be opening it. So we have already drag and drop the FSM actor. So now we are going for the composite actor. Yes. So that we will be dragging and dropping it. Yes. And then we create two sequence plotter. So this is to plot the heating rate, cooling rate, and the actual temperature change from the thermostat. So the plot is just to plot the characteristics as and when the heating is done, or as when the cooling is done. So we are going to use the plotter. So these are the four components we'll be doing it. Now for each and every component, we have to configure the complete system modeling. Now this is what the overall block diagram what we will be having. So now we are going to create two parameters. So we can search in the left hand side bar. So now we can see we create two parameters and drag and drop the parameters, parameter and parameter. So by default the name will be represented as parameter and parameter, but we wanted to change it to our own values. So we are going to give the initial temperature is one parameter. So you will take the name of the variable initial temperature. So T in the uppercase letters. So it is the syntax, or this is how the way we go for modeling. And we go for the second parameter. So double click over the small dot or press Ctrl L so that you can able to modify this. Now next thing is, so let us save this file. So we have to save this because it is not accepting the name what we are giving. So we will be saving this thing. So we will save this file. We use FSM, and when we use double click, we use noise standard deviation, because based on the standard deviation we use the value. So now in this case the initial temperature we are given as 20 degrees Celsius, and the standard deviation we are giving it as 0.2, sorry 0.5. Now this is based on these values, the entire FSM modeling will be giving its values, because the standard deviation cannot cross zero point 0.5, because since we are given the zero point 0.5, so we will have the smoother curve, or we will have the smooth temperature variation from the thermostat. So that's why we are giving this. Now we open the composite actor. So in the composite actor, first we have to give the input and the output ports. So for that we have one configuration parameter called as the input and the output port. So here we can able to add the number of ports here in this column. So we will use add. So make that as input port and show the names, add, and next thing is temperature. So input will be the heat and the output will be the temperature. So that's what we'll be giving it here. apply and commit. So once you do the commit, you can see heat in the input and the temperature in the output. We got that. So we have set the input and the output ports. So in case if you don't want to display what is input and what is output port, so you can right click and then you can able to uncheck this box. So in that case, the names won't be shown. So if you give the commit, and you can see the heat and the temperature text is not shown here, but it's always to display, it is always a better style. So we will enable the show names option. Commit. Yes, that's it. Done. Now the input and the output we have selected for the composite actor. Now we have to generate the timing waveform, or we have to generate the randomization, so that we can able to enable the thing. So for that we use a control L or open actor. Now this is for the actor. Inside the actor you can see the input is heat is there and the output temperature is also given there. Now we will search some parameters and then we can add one after the other. So first thing we add is the accumulator. We added the accumulator and then we add the Gaussian. So Gaussian is to generate random noise or random signal. So that's what the Gaussian we have added, and we have added the accumulator. Now from the Gaussian to the accumulator, we have just then along with the Gaussian, we have to add the temperature, I mean heat value also to the accumulator. So accumulator accumulates the inputs. So one input will be the heat, another input will be the Gaussian. So Gaussian will be providing the random samplings, and the heat will be given. Now we have to send it to the output temperature. So in the output temperature, we have to give one delay value. So we'll create one more, we'll add one more module called a sample delay. So in the sample delay, we are going to use one variable name. So this is a sample delay factor, and you can configure the parameters there. Just add it from the accumulator, and from there it goes to the temperature. And you can see here, so in the curvy brackets, we have this, and we set the initial temperature here. So initial temperature we already mentioned 20 degrees Celsius. So here the initial temperature will be the 20 degree, and from there that is how the way the temperature comes. And the accumulator always generate this, and we have this initial temperature tag. Yes, yes, that's how our input and the output for the composite actor will be working out. Now once it is done, we will go back. So there is a icon there. So once you click that icon, we will go back. So now our composite actor is ready. Now the FSM actor. Next thing is the FSM actor. We will again configure two ports. Now one input port will be the temperature and actor port will be the heat, because the composite actor it gives the temperature. The temperature input will be given to the FSM actor, and the FSM actor produces the output called as heat. So for that, now let us set the input and the output ports. Now as usual, we go for click add, and we give temperature, make it as input port and show the name, and add heat as the output port. Yes, you can see temperature and heats are added here. So now we have to go inside the FSM actor. We have to enable the complete states modeling. So now we will open this state modeling here. Now this is how the way we have to draw the state diagram. As we know that we have to draw the state diagram based on heating and cooling of a thermostat. So now we have the input. So we have to pull down two states. So you can see the left hand side menu, we have states. So you pull one state and another state. So you make state 1 and state 2. So you can able to change that to, first thing is heating, next thing is cooling. So the name of the state is heating and the display name also heating. In case if you want to use S0, S1, S2 like that, you can do that. The display name as S0, S1, S2. but it's always a good methodology to have the same name as the show names. The name of the state as well as the display name both can be same, then we can easily maintain it. So now we are giving cooling. Yes. So now you can see the heating and cooling state is done. Now we will make it bigger. Now after the using the control, press the control and then drag it. So heating to heating, how the state changes, heating to cooling, how the transition happen, and cooling to heating, how the transition happens. So just pull all these things. Now in this we have to based on these expressions how from heating to cooling state how the state will transfer transition. Similarly, when the state is rotating in heating, what could be happening? So for that we have to write the logical statements. Now for that again we need to go for some parameters. Four parameters we are going to use it now. So parameter 1, 2, 3 and 4. So what are the parameters we are going to have is, so one thing is the cooling rate, next is the heating rate, then heat on threshold, heat off threshold. So these are the four parameters we are going to use. So the purpose of these parameters are, suppose as long as heating is going on, that means we need to have the heating rate, on what speed the heating rate should be happening. Similarly for cooling, on what speed the cooling rate should be happening. Now see that heat on threshold. Now this is the parameter. Now use the same parameter in both the places. So copy and then paste it. Yes, now done. Similarly, next parameter is heat of threshold. Yes, heat of threshold. So next one is heating rate. Yes, done. Next one is cooling rate. Actually, when you see as per the logic, heating rate will be faster because we can heat something very easily. But cooling down is somehow it will be a time taking process. So heating rate should be higher and cooling rate should be smaller. So in this case, you can see the program, I mean the question here. Now, what is the heating rate? So you can see we are having 25 degrees Celsius, then the heater can switch on. If it is, the temperature is less than or equal to 25 degree, then the cooler can switch on if the temperature is greater than 20 degree. So more than 20 degree, okay. So now here we have given 20 and 25. So more than 20 degree, less than 20 degree, the heater will be on, and less than 25 degree, the cooler will be on. So, so we want to maintain the temperature between 20 to 25. So as long as it should be maintained. So less than 20 whenever it goes, we have to make the heater on, and more than 25 when it goes, we have to make the cooler on. So that's how we have to go. So for that we have setting the initial values. You can see here the heat on threshold is 25 and the heating rate is zero point 0.2 and the cooling rate is minus 0.1, 0.1, and heat of threshold is 20 degree. So that's what we have just given on threshold. Now we will go for first guarded thing is heat equal to, so as long as it is cooling, heat equal to cooling rate, because we are when the how the state will transition itself is, it is as long as it is cooling. So that means cooling is going on, that's why heat equal to cooling rate. But the logic here is, now this is the logic written, if temperature greater than heat of threshold, less than heat of threshold, that's what, temperature less than heat of threshold, that means the heat of threshold is 28. So then in that case if the temperature is less, then we can slowly we can cool down, because we have to maintain from 25 to 28. So that's how we cool down. And similarly for the heating alone, heat equal to heating rate, in this case you can see heat equal to heating rate, but again we have given that is the output, but god expression is, so here in Ptolemy we have one God expression. So this God expression evaluates the state, that is a state transition. Now in this case here we are trying out. So this is 25 degrees Celsius. Now how we will go with the 25 degrees Celsius? Now temperature, heat on threshold. Now the cooling temperature greater than heat of threshold, and in the heating temperature less than heat on threshold. Now in between that we wanted to try out heating to cooling, what happens. So this is what we are trying now. Heat equal to cooling rate. So because heating to cooling, obviously it is cooling rate, but what is the logic will be temperature less than or equal to heat of threshold. So what is the heat of threshold is, it is 28. So temperature greater than or equal to heat of threshold. So the current temperature is more than that, then you will just set the cooling. The current temperature is less than the heat on threshold, then you can start the heating. So simple logic. So heating to cooling, when it is come, when there's high temperature, then you cool down. When it's a low temperature, you make the heater on. So the simple logic. So that's why that the current temperature greater than or equal to heat of threshold, you switch on the cooling rate. Else, you can switch on the heating rate. Now you can see this is how the way the logic is built. The God is present and the logic is built there. Now after it is built, again we go back by clicking that up arrow. So once it is done, now we have to establish the signaling. So directly from the temperature, it is going to the sequence plotter, and sequence plotter 2 from the state modeling, it goes there, and it is joining here, and this temperature input we are going given there. So in that case, this is a composite actor where it just plots the sequence plotter 1 will be generally sequence plotter 1 is directly going from the composite actor, that is the temperature, input temperature it goes, what is the temperature, and the sequence plotter 2 displays the actual value from the state diagram. Now the number of iteration is 500 we have given as per the question. So we have to check the iterations to be 500. So 500 iterations, how it is happening. So now when I run the graph, you can see we are getting two graphs. The sequence plotter, this is the sequence plotter number 2. So you can see here point 2 is in the left hand side, you can see it is point 2 and the ending is point 1. So that means whenever it is going up, then we call it as it is the heating operation. Whenever it's cooling down, it is a point 1 is cooling operation. Now this is how the temperature variation. See that initially the temperature was something, since it's Gaussian, the temperature is sometime very high, but we wanted to cool down. Now how the temperature varies when the threshold is reaches. So this is these are the two graphs that we got from the output from the finite state modeling. Now this is how the way the circuit diagram works. Video, please subscribe to our channel, and then please comment and then share this video to your friends. So thank you very much friends. Thanks for watching.